देखेन
हो यो साइडतिर मात्रै देखिन्छ त ठिक छ अब हामीले देखिरहेको
अब ठिक छ ल त अब सुरु गरौँ याकिन्द्रजी
हजुर सर हजुर
सबभन्दा पहिला त यो नेपाको प्रेसिडेन्ट हाम्रो डाक्टर याकिन्द्रजी सेक्रेटरी हाम्रो सुजन भाइ र हाम्रो मेरो सहयात्री मित्रहरूलाई सबै होमजीबाट लिएर केदारजी सबै हाम्रो घिमिरेजी अञ्जनाजी सबैलाई स्वागत गर्दै आजको यो टपिक चाहिँ अस्ति सिडनीमा बस्दाखेरि अब केही प्रेजेन्ट गर्नु पर्यो भन्दाखेरि मैले ठिकै छ हाम्रो अहिले जुन टेक्नोलोजीमा म अहिले CSIROमा आबद्ध छु त्यही बारेमा कुरा गर्छु किनभने दिस प्रोजेक्ट इटसेल्फ इज अ माइलस्टोन प्रोजेक्ट it is an emerging technology. We also are struggling, like many other players in the world, to develop this technology into a commercial product. Despite so many of efforts, money gone into, still it's a big challenge. I thought it would be an appropriate forum to share what's going on currently and how we started with, and sort of a bit of a legacy historical perspective of how we started this project to what we are today. भनेर मैले चाहिँ यो टपिक चुज गरे हो एग्रिकल्चर फेरि नेपालको इन्ट्रेस्टमा पनि पर्यो त्यसले गर्दाखेरि धेरै मान्छेलाई इन्ट्रेस्ट पनि हुन सक्छ भनेर यो गरे अब CSIROको जम्बो टिम छ यसमा सबैजनाको नाम छैन यो चाहिँ मेजर अब प्लेयर्सहरू जो चाहिँ पहिलेबाट यो प्रोजेक्टमा इन्भल्भ भएको थियो उनीहरूको नाम यसमा राखिएको छ र अरूहरू पनि छन् यसमा तर दिज आर द मेजर प्लेयर्स इन द लास्ट 10 years we have been working together. अब आउटलाइनमा मैले त्यही भने अब ब्याकग्राउन्ड किन चाहिँ अब एग्रिकल्चरको अहिलेको ब्याकग्राउन्ड कन्टेक्स्टमा मल्चको वाज द इम्पोर्टेन्स एन्ड सिग्निफिकेन्स अफ मल्च त्यसपछि वाट वी आर युजिङ करेन्टली र वाट आर द इस्युज विथ द करेन्ट मल्च using र त्यसको फ्युचर वाट इज द अल्टरनेट अप्सन फर द फ्युचर एन्ड वाइ डु वी निड एन अल्टरनेट अप्सन अहिलेको करेन्टबाट र त्यसमा चाहिँ दुईटा एरियाज इज एन इमर्जिङ एरिया एउटा चाहिँ बायोडिग्रेडेबल प्लास्टिक मल्च र अर्को चाहिँ स्प्रेएबल बायोडिग्रेडेबल मल्च भन्छौँ हामीले र आई विल कन्क्लुड विथ द फाइन्डिङ्स अफ आवर प्रोजेक्ट्स एज वेल एज सम समरी नोट्स अब त्यही मैले ब्याकग्राउन्डमा के छ भने देयर इज अ ह्युज ग्रान्ड च्यालेन्ज एज यु अल नो देयर इज अ पपुलेसन इज लाइकली टु एक्सप्लोड टु 10 billion by 2050. Food security and food is a big issue because we need more food. And also we need efficient technology because current technology is not suffice to increase the productivity to the extent to feed that 10 billion population. The limitation factor here is we still have the same water, less water, same amount of water, same amount of land, and then on top we have to do it more ecologically, footprint, sustainable way, low carbon footprint to avoid climatic impact. It's a pressure, legislation pressure that we have to do it. So the opportunity, there is always a crisis, there is always an opportunity. So we can work on technology that can improve our water use efficiency. We can improve, work on technology that can use our nutrient efficiency, how we use and how much we use and how we release.
यहाँ चाहिँ हाम्रो होम सरले चाहिँ हात पनि उठाउनु भएको छ यसो एड्रेस पनि गर्दै जाने हो कि सर कि पछि
क्ल्यारिफाइङ
क्वेसन मात्र तपाईको प्लास्टिक भने के हो
प्लास्टिक भनेको पोलिमर भनेको
फसिल फ्युल बेस्ड सिस्टम हो त्यो नन डिग्रेडेबल चिज हो त्यहाँ त बायोडिग्रेडेबल प्लास्टिक भन्नुभएको छ नि तपाईले
अब यो चाहिँ अब आई विल गो इन्टु द सब्सिक्वेन्ट स्लाइड्स त्यसलाई डिफाइन गर्दै जान्छु म यो चाहिँ त अहिले म च्यालेन्जेसहरूलाई मात्रै गरेको अब चाहिँ त्यही हो अब क्रप प्रोडक्टिभिटी हेज इन्क्रिज बट नट इनफ टु फिड 10 billion population. A lot of chemicals are used to weed suppression. Weed is one of the competing factor to any plant growth, nutrition context. So I think with the crisis there's an opportunity, so which is good. The plastic mulch, is the legacy. If you look at historically, it was used even before Christ. First recorded use was 500 before Christ, and then 1600 people were using stone and pebbles. In 1800 they started using crop straw, residual straw, and all from the field, and then paper was used first time as a mulch in 1920. and why I'll come back to the role why we're using mulch later on. There are plastic mulch first time as a polymer, as a plastic synthetic polymer was used first time in 1950s. And in 1980s, there were issues with the plastic non-degradable, so they started working on photodegradable plastic mulch. So the first time an example of photo-biodegradable or biodegradable was in 1980s. And by 2005, first biodegradable plastic mulch was introduced into field as a trial. And still there's no product, but there are still trial going on. In 2021, most of the countries, including UNO, has passed legislation that these polymers, which are not degradable, has to be phased out. We will be using only biodegradable polymer. So currently, polymer plastic mulch accounts 10 metric ton of the total plastic consumption, 400 metric ton. I think it's more than 500 metric ton plastic we produce every year for different application, but mulch use only 10 metric ton of that. And only irony is that only 10% of the polymer or plastic gets recycled. Why we can't recycle? There are a lot of issues. The technology is expensive and it's not that straightforward. There's a lot of issues with that. So 90% of that is a waste. So why we use plastic mulch? Because it helps reduce water loss from the soil, which is very essential for plant, and it helps with suppression, control soil temperature, humidity, and microorganism population. And ultimately, by doing this, we increase the crop productivity by almost 40%. So, but just laying the plastic on the soil bed and growing the crop, broad acre or horticulture, we can increase the productivity. So it has been held as one of the revolutionary success in agriculture productivity. So this is just an example that shows that how plastic mulch is used in the farming system. It has its plus point I highlighted, but it has its own negative point, as you can see in the slides. Ultimately, the microplasticization and other factors of it associated goes into our ecosystem is not good for us. So this is very commonly used worldwide. And it's become so popular over the years that the technology has improved. The plastic mulch which we are using is currently from 50 micron to about 10 micron and is a multi-layered, and it does a lot of different color-coded plastic mulch suitable for different temperate climatic zone, and it's a wonderful tool. And it has given success from cold countries to tropical to subtropical. Everywhere you can use it, depending what kind of mulch you are wanting to use. But ultimately, it has led to so huge pollution in China. This is just an example of China, which is the largest producer and largest user of the plastic mulch. As you can see, there are issues with the plastic mulch. So why plastic mulch is an issue? Because there are very limited way you can dispose of these plastics. Our recycling, I told you, it's very difficult. And most of them goes to the landfill, incineration, burning, and in-field burial, open burning, stockpiling. And whatever you do on the right-hand side, it all goes into our ecosystem, whether into air or whether into soil or whether into water. So it's really creating, so the plastic never degrade. Non-degradable plastic lasts for about 200 to 400 years. They always remain in the soil and then slowly leach out and things like that. And some of the chemicals which are used in making these plastics, some of the toxic chemicals as an additives also leach out from this polymer, and bisphenol and things, and which are very dangerous and cancerous to this. So you can see that you are trying to dispose of, but it actually is not disposed of. It is still in the system. So I just put this slide. You will be interested to know how plastic mulch is used in Nepal. Nepal is also getting a lot of traction about plastic mulch. They are most of the Middle East को मान्छेहरू जो नेपालमा फर्केर एग्रिकल्चर खेतीमा लाग्यो, स्ट्रबेरीको यति गर्यो, हामीले यति गर्यो भन्ने जुन स्टोरीहरू हामीले सुन्छौँ, they are all using plastic mulch. The statistics are here. Primary PMAP भनेको के हो भने प्राइम मिनिस्टर एग्रिकल्चर मोडर्नाइजेसन प्र्याक्टिसेस भनेर प्राइम मिनिस्टरको लेभलमा एग्रिकल्चर पोलिसीमा इन्ट्रोड्युस गरे हो। अब त्यसले चाहिँ दे आर प्रमोटिङ दिस प्लास्टिक मल्च बिकज इट्स इन्क्रिजिङ द प्रोडक्टिभिटी नेपालमा। सो दे आर नट वरिड अबाउट द consequences, but they are just promoting as part of modernization, which is irony. Secondly, the biodegradable mulch, which can be used, is not commercially available, but it's got very high cost. So there's an awareness in Nepal. Plastic mulch they are using is bad, but they have to increase the productivity, so they are dependent on it at the moment. So that's the way forward into Nepal. Mostly in Middle Hills, Rachitun, Rakabri areas they are using. Now coming to the Homjiko question, when we talk about plastic, there are two sources of plastics. One is a conventional, which is a petroleum-based plastic. Red ma dekhachu maile. It's very dangerous. It's a polyethylene. Polyethylene ma different grades, high density, low density, different grades of cross-linking makes it different purpose and application. Then polypropylene glycol, polystyrene, polyvinylene. So these are very notorious polymer. They never degrade. But they are very useful. They are very useful as a mulch, not only for mulch, for making bottles and this and greenhouse, for every applications, from household to industrial applications. So this is dangerous. And then if you go on to the top, you can see the bioplastics. Bioplastics, which are biomass based, just a crop residues. We call it as a bioplastic because they are altogether cellulose type material. All this straw, they are all cellulose and it's a biomass. And then when we refine that biomass further into starch, cellulose, alginate, we take out chemicals from them. They themselves are polymer. Also very high molecular weight, and we also call them bio-based biodegradable. So this, I think the renewal biodegradable is a confusing kind of sometime, but they are both biodegradable, bioplastic are renewable sources, and then some of them are also available from petroleum-based. At the lower bottom, as you can see here, at the bottom here, PLLA, polylactic acid, polyhydroxyalkanate, polycaprolactone. These are derived from synthetic polymer. They are also available from plant sources, but they are very expensive to get it from the plant. So we get it from the plant, but because they are biodegradable, so they are still called bioplastic, but their origin is from the petroleum-based. So not all chemicals are bad from petroleum sources, but very limited amount of chemicals are there who people are using as a bio-based because they can't get it from the plant as a
एउटा कस्तो छ तपाईँ यो तपाईले जुन बायोप्लास्टिक्स भन्नुभएको छ नि त्यो चाहिँ साँच्चीकै हामीले हेरेको जस्तै प्लास्टिक फिल्ममा कन्भर्ट गरेर अथवा प्लास्टिक पार्टिकलहरुमा कन्भर्ट गरेर चाहिँ भने हो कि एज अ जेनेरिक नेम तिनीहरुको केमिकल प्रपर्टी पनि प्लास्टिकको जस्तै हुने भएकोले हामीले प्लास्टिक भने हो भनेर त्यसै नाम दिए
They can be processed into like a plastic film. Bottles haru अहिले तपाईले सेफवेमा हेर्नु भएको छ नि यो के नाम दिएर यो ठुलठुलो कम्पनीहरुले ल्याएको छ. They are also biodegradable plastic, so they can be extruded like a film by processing. Polyethylene जस्तो.
So हामीले बायोप्लास्टिक भनेपछि तिनीहरु प्लास्टिकको फर्ममा कन्भर्जन भइसक्या हो.
बायोमास भनेको चाहिँ तपाईको सेलुलोज भयो, स्ट्रो भयो, एज ए हो, तर त्यही बायोमासलाई प्रोसेस गर्नुभयो भने प्लास्टिक मैले किन वर्ड राखे भने मान्छेलाई सम्झाउन सजिलो. जनरली वी कॉल इट बायोपोलिमर टेक्निकली.
हाम्रो पराल भन्नुस् न, पराल स्ट्रो हैन, तपाईको त्यो सेलुलोज इत्यादि के भन्थ्यो पर्यो, त्यो परालकै रूपमा राख्यो भने प्लास्टिक त भएन नि, के भयो?
त्यो भएन. प्लाइज अ बायोमास, दे क्यान बी प्रोसेस्ड इन्टु प्लास्टिक्स.
त्यसले प्रोसेस गरेर प्लास्टिक बनाइसकेपछि चाहिँ त्यो परालबाट डिराइभ गरे हुनाले तपाईले त्यो बायोडिग्रेडेबल प्लास्टिक हो.
ओरिजिन फ्रम द नेचुरल सोर्सबाट आएको हुनाले, प्लान्ट बेस्ड ओरिजिन भएको हुनाले वी कॉल इट बायो.
All right. Okay. Thank you.
Okay. अब यो मैले यो देखेको when we are talking about mulch film has to have certain attributes. त्यही मैले अस्ति भने अघि नै भने जस्तै soil temperature, productivity increase गर्न, soil temperature maintain गर्ने, यो सबै weed control सबै कुरा गर्नको लागि these are the standard key features you have to have in the mulch film. Most of it has to be non-toxic when it degrades. When we call it bio-based, they are biodegradable. They degrade into soil. So when they degrade, unlike non-degradable plastics, it's not micronized. They really degrade into smaller component or byproduct of individual chemicals, biodegradable. So they have to be non-toxic, friendly to soil, and they have to be low cost. I think the whole technology is driven by cost. If you have the best technology, but if the expense is very expensive, farmers are not interested to use. They would rather use chemicals and low cheap chemicals and still use non-degradable plastics, but not this one. So, and you have all of these things to prove that your technology works. There are standard guidelines, ASTM protocols. You have to get certified your material that it is biodegradable and all sort of things. So it has to be readily available, and all these things are very important part of mulch property.
Sorry to interrupt, sir. Kedar sir le kehi bhanna khojnu bhayरहेछ.
Yes, sorry, Rajaji. You पछाडि सोधेका हुनुहुन्थ्यो तर but while you are on the naming issue, bioplastic. So why do we call it bio? I mean, not a plastic. Instead of saying plastic, can we give something name? So it's kind of probably plastic has a bad name. So
yeah, that's true. I should have used polymer instead of plastic, but but for the common men don't understand what the polymer is. So I thought I will put plastic. It generally is a trade name kind of, but people nowadays you look at technical papers biopolymers भन्छ तर चाहिँ यो कमन्समा चाहिँ हेर्दाखेरि प्लास्टिक मल्च भन्छ, अझै पनि PM भन्छ, पोलिमर मल्च भन्छ कहीँ ठाउँमा, तर अलिक कमन चाहिँ त्यसरी युज गर्छ.
अलिकति bad because the plastic has a bad name.
Very bad name. And all the polymers, even if you change the name, doesn't change his reputation. Even if you call it a non-degradable polymer, it's still as bad as his non-degradable plastic. It's the same thing. एउटा न्वारानको नाम, एउटा चाहिँ के अरे कमर्सियल नाम.
All right, thank you.
अब यो biodegradable plastic mulch को कस्तो छ भने, because it's plant based, it's very expensive. So initial market, if you look at, was very small in number in terms of dollars value. But now because it's getting traction, it's getting popular, and it is meeting those criteria, and people have found ways to improve the technology and make it work. So the compound annual growth rate is 8.69%, and it looks to be 72 billion, almost $75 billion from in 5 years time. So whereas the non-degradable plastic mulch is 10 times of this. So so you can see there's the technology is supported by the market. So that's a good news. They are looking into it as an option because it will be ultimately phased out. And when it's phased out, you should be prepared what to use as a next option. So people are spending a lot of money and getting a lot of trials to make it happen in that sense. Again, there's another confusing sometimes. People say, what is biodegradable, what is compostable? All biodegradable polymers are not compostable, but all compostable material are biodegradable. So as I have I've written here, the biocompostable भनेको मतलब चाहिँ it has to once not only break down into carbon dioxide and water as a non-toxic product, it also leads into a certain degree of biomass, which becomes part of the soil nutrient. So then it's compostable. Whereas biodegradable just break down the products. They are non-toxic, but they may not be nutrient rich to add to value to the soil. So there's a subtle difference. People get confused, but it's very difficult. The traction is now everyone is trying to achieve compostable, because that is the ultimate goal for all the people who are working in biodegradable polymer, is to make compostable mulch. When we talk about biodegradable, they mainly degrade by many ways. I will come that later, by hydrolytic, by UV, by temperature, by thermal, everything. But most of them, because they are bio-based, they are degraded by microorganism. And the microorganism, they break down polymers into smaller chains, because these are very hyperbranched, long molecular, high molecular weight networks. So they have to break it down before the microorganism loves to chew it. So they break down the bones and then they start chewing it. And there are two ways it happens. One is, we call it aerobic biodegradation, where it is in the presence of oxygen, and microorganism in the presence of oxygen breaks down this polymer and mainly reuse carbon dioxide and water. Anaerobic production means biodegradation means there's no oxygen, there's less oxygen there, but still certain microorganism still degrades these polymers, but it produces methane gas also, whereas in the aerobic there's no methane. In this case it is a methane gas because lack of oxygen. Methane, as we know, is useful as well as very unfriendly for the environment. It is toxic to environment. We use methane gas in household, in cooking this and that kind of. Even people have refined the purity of this methane gas to almost 99% to be used for even medical other applications as well. But nevertheless, it is not a desired. Methane is not ticked as by regulatory approval for as environmental friendly this thing. So these are the mainly two ways microorganism will degrade all the biopolymers which are used in the mulch film. So when we were given this in CSIRO, when I was working onto a project, and then I was asked to join this project, and the initial brainstorming was we should be working to develop biodegradable plastic mulch, because I was working in biodegradable polymers for medical application that time. They said, why can't you use in plastic mulch? We looked into the literature and we found everyone is ahead of us. Even in 2000, European had a big funding, and in 2008, they have already tried some of the polysaccharide-based biopolymer into the field as a mulch. So, and they are they even sprayable one. And even the 2013, there were more people coming in. So we were very confused where should we start unless we start something new. So we designed our own polymer, which is polyurethane based. It is not bio-based, but it is biodegradable polymer, and it's made from the chemicals which are driven from plants, some from petroleum sources, but we combine them to make a polymer with the functional structure that makes it biodegradable. So, and the advantage we had was, this is a synthetic way it is designed. It's not a natural. It's very difficult to functionalize natural polymer, starch, cellulose. They are already built in structure. Very difficult to play with the chemistry. But when we design our own polymer, we can change anything in the structure. So that gives an advantage to control its degradation, its other mechanical properties. So we thought we are in a better position. So we developed this first technology in 2014. And the idea was that, as you can see, before I told you, the mulch film ko kasto huncha bhane, as you can see, the water is lost in different ways, by evaporation, by infiltration, by leakage. These are all zones. Instead of water going towards the root, any water which is spread on the soil bed is lost. 80–90% of the water is lost because of the capillarity action of the soil. So soil cannot retain. So as a result, we thought if to stop this, we have to put something on the top, so that even if you cannot avoid the leakage, but at least 50–60% of the water which is lost by evaporation, if we can bring them towards the root and stop the evaporation, it will go through the root into the plant, and that water is used with the carbon dioxide to make carbohydrate, and thus will increase the plant yield and crop. So we call it a transpirational. So we call our technology called transpirational. So we were trying to retain the water, bring it towards the root of the plant. And how we do it? And okay, so the target property we were given, we looked into the literature, and the people who were interested to support this project, they said, unless your films do not have this property, it's not going to make any product into the market. So it'll be a futile exercise. So the most challenging was the water vapor transmission rate. For biodegradable polymer, because when they come in contact with the moisture, they start degrading. So you have to retain the property in a way so that it still maintain that loss of water. And then the other challenge was it should stop synthetic photosynthesis radiation going through the plastic film, because that will help grow weed also under the film. So it has to have these properties similar to polyethylene non-degradable plastic mulch. If you cannot meet these properties, it's no point working. That's why most of the technology who are working before us, they have failed because they are still struggling is to improve this property so that they can make it work. So it's not, and has to be cost effective. As I said, bio-based are very expensive sources of material, and how to make it cost effective is to use less of it. And to use less of it, you have to develop technology which makes less use of it. So there are a few challenges we were told to do these things. And then the other things, we also did a lot of modeling to say, okay, even in the bed, why do we need to cover the full width of the bed? We can work out a modeling instead of 60 centimeter. If you can work out only 50 centimeter where the plant root is located, where the water loss is coming from. If you, through the drip irrigation, the water is going only through the root nowadays, and then that water will also evaporate from nearby. So if we cover about only 50 centimeter trip, on the bed, it will still do the job. So it's in one way of reducing the use of polymer, in still achieving the same size. So there was some modeling work was done. As you can see on the right hand slide, cumulative water loss was very high on the 60, very less with the 60 centimeter coverage, whereas as you go up, it is less and less, and the top line is a blank where you have maximum loss of water without any coverage. So when we worked on it, as I've said before, our polymer initially was a very high vapor transmission rate. This is 1,500 gram per square meter, which is very high, especially bio-based polymers. We require only 10 gram. Per square meter water loss to compete with the polyethylene mulch. High transmissivity is polyethylene mulch is less than 0.1, whereas most of the biopolymers are around 4.5. So that means all the light is going through the polymer, and then the weeds are growing. So you're not controlling basically. The cost is 3 times more than the plastic mulch. So we were given this task, but a lot of challenges in meeting these target properties. So we had to do something clever chemistry to make that happen. So this is just a slide which shows that how when you spray any polymer, especially sprayable means it's a solution. So when you spray any solution, the reason why we went to solution is because it's cost effective, it's easy to convenient to use, whereas the preformed plastic mulches have been tried, but they are sort of not very strong in mechanical properties like polyethylene mulch. So people are still expensive. So we thought we'll go sprayable. So, and this is just a trial that when you spray any polymer, it should form a barrier like this. But what happens in real life is that when you spray the polymer, this thing goes into leakage. Most of them, if it's not a good film, it goes into the leakage, and the water is evaporated. So this is the kind of a challenge, with all these things. So we had to work 3 years to improve all of the properties, the chemistry, the everything. There's a huge team of people modeling to, surface scientists to chemists, more formulation to us, polymer design. So we ultimately made this our technology launch for the field trial, in 2020, I think 2018, after 4 years. And as you can see, we spray our polymer, and then we were able to achieve most of the target property as desired. We are still struggling in terms of cost, but otherwise we have achieved 80% of the success in the technology. So how did we do? The chemistry, as I said to you before, this is just a typical schematic structure of our polymer chain. As you can see, there are different color-coded abbreviation and the wordings, and they represent different group. And because it has to be water soluble, polymers are never water soluble. So to make it water emulsifiable, or not water soluble, even to go into water as an emulsion, you have to put some ionic structure so that it goes into water. So we played with lots of ionic structure in different part of the polymer, and the polymer itself is a two-phase structure. I'm not showing here where and how we put it. It's just a very blatant, very simple design. Otherwise, it's a very complicated design. So we put in a lot of cationic. Soils are mainly anionic polymer. So we were designing both anionic and cationics and deuterionics, having both ion, just to see that it works that way. And so when we tested after 4 years, we found these are some of our properties. We were able to achieve most of the properties, but we are competing with the cost. The cost we could bring down was $1,200 per hectare if you spray 0.5 kilogram per square meter. But we realize our polymer needs to be sprayed more, about 1 kilogram to 2 kilogram, which is 28% solid content in the water. So we are spraying only 20% weight percent, but we need 1 kilo of that solution sprayed. And the cost is incomparable with the polyethylene mulch, which is currently $1,200 per hectare, including incineration, transportation, laying, disposal, everything. The polyethylene mulch, if you are using, it costs you $1,200. Whereas our one, you just spray, you don't need to remove, you don't need to do anything, you just go and spray, it goes into the soil. The cost is still 1,200. And is protected by a family of patents. So the degradation, as I said before, aerobic or anaerobic degradation, we built into polymer the structure which undergoes hydrolytic, oxidative, thermal, UV, every degradations mechanism is when it feel exposed to, and it breaks down into ammonia and amine compounds. Amine compounds are supposedly a nutrient rich in nitrogen, is add value to the soil. So it is seen to be more complementary rather than this thing, and carbon dioxide and water. So these are the mechanisms we had established to convince our partners that these polymers are non-degradable, degradable with the safe byproducts. So this is kind of an emulsion. When it goes into the water, the polymer, you got a lot of things there. There are a lot of additives are there, surfactants are added, and not only polymer, if you make only ionic structure, it will go straight into water. It doesn't work that way. You'll have to add a lot of additive, lot of surfactants, and we were using black pigmented for the weed control. We to use carbon particles. So the problem with any emulsion, burning ma gaera paint pani kinnu bhayo bhane, it has an expiry life. If you open the can after 1 or 2 years, there's a settlement issues. And then you have to stir it, but at some point after the expiry, it is not usable. This is a typical, so the storage life is a big challenge. The reason why is that in emulsion, the fluctuation, the particle size, the charge interaction, depending the hysteric factor, electrostatic charges and all, they are very important to maintain, but at the same time, if you lose any of them, it start flocculating. And then we start flocculating and then coalescence, it becomes big particles. And then it ultimately leads to the phase separation. So this is the challenge. So it's not only formulating the polymer and making it emulsion, its storage stability is very, very important. Otherwise, this becomes more expensive if it is to be stirred when you are using it, or it has to be just usable. Nowadays, we are talking about making into a powder so that you don't have water is very expensive in Australia. So even if you have 28% formulation, 80% is water. Water is expensive. Transportation cost is very expensive. So we are trying to make it into a powder. So you take this powder, go to the field, then you mix the water as much you want, rather than making 28% in transporting cost. So the other these things, the property I've shown is very important because the tensile, it has to have a very strong tear strength and the tensile strength, because a lot of wind, there's a lot of soil surface are very rough and things. So you really need to have a very strong film, and these are the minimum requirements you have to have. So we were able to achieve those tensile strength, and elasticity is very important because when you spray the polymer, it will move onto this contour of the soil surfaces, and it should move very fast in a way that it continue to form a network of film rather than film here and there and discretely and not continuous film. So these are elasticity is very important, and the modulus, the softness of the polymer, because if it's too hard, become too brittle after it is dried. And then it will break up easily when it absorbs the moisture. So it has to be still elastic once it cured, dried after spraying. Then it is to be soft and then continue to do the job. So these properties, three properties are important. But before you go to the field trial, you are required to do pot trial. Because you just field trial is too expensive, and then so these are standard ASTM protocol. We did the pot trial to see how much water is lost using the same soil which from the field and treated under ASTM condition. And when we did this, we also wanted to know how much polymer we need to spray. The viscosity was very important. How much viscosity we have in the polymer, the thickness, so that when you spray, the capillarity is reduced, and we worked out a viscosity number that I haven't mentioned here, but it was something like 500 millipascals per second kind of things. So that viscosity we optimized. Then we wanted to know how much polymer we should load, 10 weight percent, 20 weight percent, 30 weight percent, because if you go higher, it's good, but it's expensive. So we trying to find out the lowest amount of solid content, and we worked out that 20 weight percent works best in two different type of the soils, which we were interested initially for the horticulture crops in agriculture in Uchuka and Griffith. The reason why we were interested in horticulture was horticulture is a very cash-driven, very high-value market product. People are ready to purchase at any price. So you can get a lot of benefit, commercial benefit if you focus. And then weed control was the focus initially because they don't want to have spray pesticides. So our technology in the first 10 years was focused on horticulture, controlling not only water, but also weed. And mostly in the Victoria, the trial was done. And then we compared it with the plastic mulch. As you can see, the plastic mulch at the bottom is this one. This has almost no water loss. And then this is our polymer, which almost has got, 40% of the water loss, and this is a blank. So we were not very close to the polyethylene mulch, but we are very nearby. We could reduce at least 60-65% water loss. So this is good. It has to be demonstrated through the pot trial. And this cumulative, we did it for 4 weeks trial. Kind of thing. And then you have to also do aerobic biodegradation. CSIRO has got a very excellent facilities where we looked at the biodegradation, and the cellulose was used as a benchmark because it degrades very fast. So we used it, and our polymer degrade over as you can see, the bottom ones is our polymers. So it is not abrupt loss. Or degradation. It is a very slow degradation. That is what we want, because when polymer degrades, it loses its property, all the properties which we want to retain, the moisture, the synthetic radiations, and all sort of the barrier property. If it degrades too fast, it won't retain, and the polymer is not useful. So we wanted a constant slow degradation, and that is what we saw our polymer is doing. And our polymer degraded only 30-40% compared to almost like 60, even 85% 80% of cellulose under aerobic condition. And the calculation we did was that we work out a theoretical, and it is done in a jar, in a very well set up container, where we calculate the theoretical amount of carbon dioxide from the solid mass of the polymer used and the content of carbon present into it, and multiplied by molecular weight of carbon dioxide and carbon, and then divide by the treated carbon dioxide. So these gases are collected in the jars and automatically fed into the balance. And then the whole degradation process of 3 to 4 months is fed with continuous water and all sort of under ASTM condition. So we know how much theoretically carbon dioxide is generated, how much control has generated, how much our polymer has generated. So we can work out that, and we're very happy. Our polymer is degrading as desired with a very slow constant release of degradation. So the next we were asked to do before trial was the ecotoxicity and toxicity test. So the toxicity test, we're doing two different types. One, germination test. So we use two different type of plant, monocotyledon and dicotyledon, because most of the vegetable crops are either monocotyledon. Even the plants are, either the wheat are monocotyledon, whereas most of the other crops are dicotyledon. So we wanted to try both type of plant. We were looking at the germination, and with the constant flux of light over a period of time, and everything is under control condition. And then we also looked at, after not only counting the number of germination, but also we weighed each of the germinated plant, dried it, weigh it, and any defects into it. So it was all done by the microbiologist expert. So it is a very cumbersome process, but it is done in CSIRO very easily. And we also did the toxicity test, which is called ecotoxicity, which is also like an earthworm test. So we put earthworm, which is the most friendly soil, insect, whatever we call it. We mix it with the soil, one with a blank and one with a polymer powder, mix it and put it into water and put it into the jar. And after routine of 14 days, we take out the earthworms, look at their physiology, morphology, their any defects in their body and the death and kind of thing. So these are the standard tests we had to do before we go to the field trial. And also we did a weed control trial. So in Uchuca, we went in, we just sprayed. As you can see here, this one is our polymer treated, the strip with the black one, there's no weed growing. Whereas the other, where there was no spray of our polymer, you can see a lot of weed growing. So our polymer does reduce 80% of the weed growth. It's not 100%, but it clearly showed that it is doing wonderful, stopping the power radiations and controlling the weed underneath. So it was a great results. So then after all these trials for 4 years, a lot of works, we were asked to go to the field. And then we went in the field in 2018. This was in Griffith, and that time we had not made black pigmented. We just wanted to see water retention, the first trial. And then we spread it and we measured the water. And then later on, we made the pigmented black version for the weed control. And we did a lot of trials later on with the pigmented on cotton, sorghum, melons, tomatoes, mostly in Victoria. So, and then I'll come up back to the results. We also went to Indonesia last year to do a tropical weather, because that's completely harsh weather. Australia's soil conditions and weathers are okay, very friendly to mulch. But if you go to country like Indonesia and other places, you have a hurricane, rain, wind, everything. So, not friendly. So we wanted to do the trial in Indonesia also, and we did last year on cabbage, chilies, and things like that. So we wanted to know, after we did the field trial, we wanted to know how much polymer has degraded in 3 months' time or 2 months' time. So we picked up the polymer traces, whatever left out in the soil, and then we looked at the molecular weight. And as you can see, after 2 months, the molecular weight from 250,000 was almost like a 5,000. So polymer degrades by chain secession, and then slowly chain degrades to very low molecular weight. Ultimately, ultimately, once it is very low molecular weight, enzyme takes over and then breaks down very easily into until such time there's a hydrolytic degradation, oxidative and UV degradation helping initially to break down the polymer chain, and comes to a size where the microorganisms are very friendly and they start chewing, and then the rest of the degradation is exponential. So in 2 months time, we were very happy that our polymer is degrading as we expected. So, and then the other important thing was the regulatory approval in Australia. Globally, they are very interested that how much of the polymers we're using has bought heavy elements like the lead, arsenic, mercury, zinc. These are cadmium. These are some of the very toxic, nasty chemicals we use in polymers, some way or the different chemicals, even pesticides and all things like that. So formulation uses different kind of elements. So we were testing our elemental analysis. We were given go ahead. So there was no toxicity. We didn't find any of our polymer breakdown after the soil testing. There was any heavy element trace. So that was good. So now we compare the cost. Of the 28% formulation from the horticulture pigmented, we said, okay, what's the cost? The cost at the moment, as I said before, is roughly plastic mulch is 1,400 and has increased because of the levy by the government recently. And the preformed biodegradable mulch, which we are not doing, is about 1,400. Our is a 1,200. The reason we are only spraying on a very small part of the bed, and we are also using effectively, and there's a technology improvement on how to spray, inkjet spray, atomized spray, all these. There's a team who is working on to optimize the spray and to do all these things. So this is the slides where, as you can see, traditional polymers, the plastic mills, you have got 3 red lights, whereas the other sprayable polymers are also okay, but there's 2, whereas the BSF film, eco, which we are using even in the grocery bags, and they're also using not exactly, but different formulations. They still have got a lot of issues here, as you can see, whereas our polymer, you can see, there's all green. So whether it's a biodegradability or ease of application or the benefit, I think we are much better. We are still in the phase of optimizing, but this is what it is. So after we went to, our interest was in horticulture. We looked at if the value of the cost of the polymer is high, how much farmer can recover. So initially we targeted tomatoes and then cotton. These are the 2 most famous vegetable crops, and the other crops in Australia. The total is the 32 million hectare, and the market is $1 billion. So if you can replace this thing, you will be churning out $1 billion, 100 million from the cotton and the all together. So globally, if you only capture the cotton and tomatoes, it's about $36 billion market. So we were focusing on 2 products and go globally, firstly in Australia and then go globally. So we went to the company creation. We wanted to establish, because CSIRO doesn't do any startup nowadays, so it's a different proposition. So we have to look for venture capital or angel investor or the company. So we found a company in Indonesia. The CSIRO chip in the technology, and there was a manufacturer in Australia. We all together working to develop a company. The company didn't happen after 2 years of great exercise, and there was a lot of agreement. The company didn't go ahead because the cost is still very high, and the results are not still very convincing, very conclusive, reproducible in different soil conditions and different crops. It may work for one or not, and the 80% is not satisfying. They want every results to be consistent, 100% reproducible, like a non-degradable plastic mulch. So the company creation is a halt. So we made a business case. Initially, we were very successful. We justified what's the problem, what's the solution, what's the market size, and what's the value proposition. So it had gone into company creation, and we were almost there to launch. But then the venture capital, the one who was putting money, pulled out and wanted more field trial results before they do these things. So this was a bit of a tragedy. So when we were struggling to find and create company, we were lucky to get traction from GRDC. GRDC was watching us. It's a Grain Research Development Corporation. They were watching us. They said, oh, well, hold on. If you can work for us. Our product concept is different. We want still sprayable mulch, but we want it only for water retention for the broad acre crop in wheat and barley and in the Western Australia. We're not interested in weed control. So can you reduce the cost? And can you make it cheap? $200 per hectare from 1,200. So we had to completely reverse the game and change the formulations in a way. So we were using the same raw material in different way in designing, and our design was basically on our synthetic polymer. But now we are going backwards to the bio-based polymer. Cellulose has become kind of hard. So, but anyway, this is very confidential, so I can't disclose the details here. This project is for 3 years contract until 2027. So the current focus is we are focusing on broad acre crops in Western Australia. We are only for water retention. We are developing new hybrid composite formulation with a very reduced cost. I think we are going to field trials after March, April this year. The first milestone is in March, April. Once GRDC approves, and we're trying to write a provisional disclosure of invention of these new formulations. I cannot disclose any details, but that is the ultimate. We hope to go after the first milestone approved. We're going to go to the next trial in the Western Australia next year. These are some of the old papers, and we have got family of 4 patents, a few more coming up. So these are the new publications in the pipeline, but these are some of the old papers we published. So conclusion, I think our technology with the GRD support is going in a different direction, but water retention for a drought country like Australia. Australia is a food bowl country, produces largest number of food crops, wheat, and so they need to retain water, especially in Western Australia. Very little water, and when it rains, you have to capture that water at any cost, just to germinate for the first few weeks. After the plant is germinated, then plant is able to withstand any sort of less water. But they are really deeply interested. Field results are very promising. Not very 100% like polyethylene, but it's very convincing. And we have made it in tons quantity, these polymers. So it has to be manufacturable in a cost-effective way. If we can't manufacture, if there's the issue of this emulsion and the stability, and also you cannot make it, then there's a problem. Emulsion chemistry is very strong worldwide, as you can see. All the paint industry and every industry, formula, even agriculture, they are using all the pesticides. They are all emulsion chemistry. So, and commercialization of technology is in progress. So with that note, thank you. I might have taken much more time, but I thought I'd give you a total perspective of the technology. Thank you.
Thank you, Raju sir. Very nice presentation. Yeah, floor is open for the questions. Yeah, it's a very interesting presentation, definitely for us. Please, anyone, if you have any questions.
म सुरु गरौँ है त
हजुर, हस्।
उदय